Right, okay, let's have a look at these questions that I set you for homework, okay? Starting with the foil, the kitchen foil one, all right? You're given a value for width, you're given a value for length, and you're given an uncertainty. And that uncertainty is the resolution of the instrument. Question says, for 2 marks, determine the area of the foil and the percentage uncertainty. So finding the area is easy, but some of you lost a mark here because you didn't put the unit, okay? So it's width times length. (600) and it's centimetres squared. So some of you missed that because you didn't have the centimetre squared. There's often a unit mark, not always, but often there is. Okay, now you need to find the percentage uncertainty for area. So you need to find the percentage uncertainty in the width and then the percentage uncertainty in the length first. And then because area is width times length, the percentage uncertainty for area is the percentage uncertainty for width plus the percentage uncertainty for length. Okay, so percentage uncertainty for width is 0.1 over 20.0 times 100, and that is 0.5%. And percentage uncertainty for length is 0.1 over 30.0 times 100, and that is 0.3%. Okay, and remember, significant figures for percentage uncertainties, just one significant figure. But what I would always do, perhaps, is to, don't round things too early, okay? Right, so percentage uncertainty for the area is that plus that, which is 0.8%, and that's your second mark, all right? Now then, to increase the accuracy of calculation, have you folded the foil 4 times and measured the thickness of 16 sheets? He measured the thickness in 3 different places and found the following results. So he's got a range of readings here, but this is not the thickness of a single sheet. This is the thickness of 16 sheets. So to find his 3 thicknesses, before you can find the mean, you need to be dividing all of this by 16, okay? And what I have done here is I have kept the figures as accurate as I can without being silly, and rounding at the end. Okay, so how do you find the mean of 3 numbers? You add those 3 up and you divide by 3, and the mean thickness comes at 0.01875 millimeters. Okay, now let me have a quick look on the mark scheme and see what they're accepting for that. The mean thickness, so let's see what we got. We got 2 significant figures here. We got 2 significant figures here. 2 significant figures in your answer would be 0.019. All right, now that's the very best answer. 2 significant figures, the same as is given in the question. All right, and the mark scheme is saying it will give the mark for that, right? And it will also give 0.0188, okay? But that's your best answer, all right? And all this is still in, let me just double check, thicknesses. Yeah, all this is still in millimeters. Okay, now we need to find the percentage uncertainty for the thickness, okay? So we're not using the resolution of an instrument for the thickness, we're using half the range of values. So the uncertainty for thickness is the max minus the min over 2, and then we can work out the percentage uncertainty, all right? So the maximum value for a single thickness is, that's my biggest number there, it's 0.020625, take away the smallest number, which is that, 0.01625, and that's over 2, and the answer for that is 2.875. Hang on a second, let me just check that. I think I got that wrong. Hang on. 0.020625 minus 0.01625 equals, divided by 2 equals 2.1875 times 10 to the minus 3. Okay, that's my answer for the uncertainty of thickness. And then to find the percentage uncertainty, do you remember you use the uncertainty divided by the mean value. So it's uncertainty divided by the mean value and times it by 100. Yeah. So that is 2.1875 times 10 to the minus 3 over, where's my mean value? This one here. Do you know what? I think I'll put the more accurate answer in there for now. And that comes out at 12%. Okay, so there's a mark for the mean thickness and there's 2 marks for the percentage uncertainty there. Right, that's difficult. It is difficult. There's a lot of data, a lot of numbers there to handle. What's it saying? Actually, it'll accept any number of significant figures for this. You could put that as 10, because if you're thinking, oh, she keeps telling us it's one significant figure, you could put that as 10. But you know, it's 12 or 10 on the mark scheme, and there's no mark lost for significant figures in this case. I know, sometimes they do, sometimes they don't. Right, find the volume. So if we've got the area up here and we've got the thickness, we times the 2 together to find the volume, right? But the problem with it is your mind's been blown up here. Volume is area times thickness. So it's easy. Don't assume just because you've got completely bogged down in the first bit that you're done with the question. All right, keep going. So it's 600. Hang on a minute now. That's centimeters. Yeah. So I need to turn my thickness. Where's my thickness value? Yeah. I need to turn that into centimetres, don't I? So that is 0.019, and what have I got? I've got it in millimetres, and I want to turn it into centimetres, so I divide by 10 or times by 10 to the minus 1. I'm just going to stick this in my calculator, all right? And the answer for volume is 1.125 centimetres cubed. Okay, that's your answer for volume. And the mark scheme, let me just check on the mark scheme. I'll attach the mark scheme for you to look at it. Yeah, there's a couple of different ones there. You could have 1.125 or 1.140, depending upon what your rounded value was for the thickness, okay? So there's a mark for that, which is a lot, isn't it? Particularly if you've messed up the units. And then you also need the percentage uncertainty for volume, all right? So what's the percentage uncertainty for volume? It's the percentage uncertainty for area plus the percentage uncertainty for thickness, right? Did we work out for area? Yes, we did. So it's 0.8%. Hang on a minute, have I? Yeah, it's 0.8% plus 12%, and round it up to 13%. Okay, that's that bit. So a bit more on this. Yes, there is. Okay. So it gives you a mass now and asks you to find a density. So what have we got? Density is mass divided by volume. The mass is 2.81 grams, and dividing by the volume, which was 1.125 centimetres cubed, and that comes out at 2.5 grams per centimetre cubed. When I look at the mark scheme, there is no error carried forward for this at all, which is quite tough, I think. So there's a lot of work here. A lot of you got quite low marks on this because you went wrong earlier, and you haven't gained anything here because there's no error carried forward. And then what's next? Determine the absolute uncertainty. So we've got the percentage uncertainty, haven't we? Did we do that? No, we did the percentage uncertainty for volume. So the percentage uncertainty for density is that volume one, which was 13%, plus the percentage uncertainty for mass. Oh, I need to do that then, don't I? What's the uncertainty for mass? The uncertainty for mass is 0.01 over 2.81 times 100, and that comes out at 0.3%. So it's 13% plus 0.3%, and that is a total of 13%. Percentage uncertainty for density. And now we need to find the absolute. So what's 13% of 2.5, right? 13% of 2.5 is, hang on a second, 13 divided by 100 of 2.5 equals 3.25. 3.25 grams per centimetre cubed. So let me just double check the mark scheme. That's not right. 13% of 2.5. Hang on, I've made a mistake here. 13% of 2.5 equals, it's more like it, 0.3 grams per centimetre cubed. Okay, so if we wanted to, we could quote it as density equals 2.5 plus or minus 0.3 grams per centimetre cubed. Okay. Lastly, for 2 marks, this should be an easy 2 marks. Which are the measurements now, right? So we're looking for measurements. We didn't measure volume, did we? We calculated volume. Which of the measurements contributes most to the uncertainty? Which gave us the greatest percentage uncertainty? Here, the thickness, yeah? So the answer is thickness. Are you asked to say why? I'm going to put why, because it's the greatest percentage uncertainty. And how could you reduce the uncertainty? Well, there are a few different options for this. You could fold it more times. So you're measuring, instead of having 16, you could have 32 thicknesses. Yeah, so you could fold it more. That would get you second mark. Or you could use a higher resolution instrument for the thickness. Or instead of using foil, you could use a thicker piece of aluminium. Okay, so it's 3 different variations of a correct answer there. The total was out of 13. Most people did, I don't know, I don't think I gave much more than 5 or 6 maximum. This question then was a bit easier. The ball bearing. Calculate the density of the ball bearing and show that the percent, that means calculate the percentage uncertainty and get the correct answer, basically. All right. But when you're showing that, it's important that you state the formula and that you're quite clear. It's almost it's like writing a worked example, like I would do on the board. Okay, so what's the density? Density is, like, the mock volume's already done for us. You don't need your 4/3 pi r cubed, so it's mass over volume, right? Which is 45.4 over 5.6, and that is 8.1 grams per centimetre cubed. So what's your significant figures again? Right, look, how many significant figures in volume? Ignore the uncertainty. That's 2 significant figures, right? The mass of the ball bearing is quoted in 3 significant figures. But what you would do is look at the least accurate one and go with that. So quote your answer to 2 significant figures. At a push, they'll accept 3. All right, but that's the best way to do it. That's your first mark. 2 marks for the percentage uncertainty. So if you want the percentage uncertainty for density, we've got to work out the percentage uncertainty for volume and the percentage uncertainty for mass. And these are uncertainty over the best answer times 100. And this one is 0.5 over 45.4 times 100. And the volume comes out at 3.6%. I've left that as 2 significant figures for the minute because I'm going to add them up. And then the percentage uncertainty for density is 3.6 plus 1.1 is 4.7, which is approximately equal to 5%. Okay. Find the absolute uncertainty. So that means find what's 5% of 8.1. What's 5% of 8.1? You can either times it by 0.05 or you do 5 divided by 100. Or it could be 4% of 8.1. I would use this one, right? Use your better answer rather than the approximated one in the question. They're doing this to help you because the idea being that if you got that wrong, you can still use the 5%. And in actual fact, the mark scheme does give 2 answers. Okay. So now you've got a table with 1, 2, 3, 4, 5, 6 metals and 6 densities. And of course it asks you, what are the possible materials? And explain why you can't say